Okay, so welcome back to brand new videos. Today we are going to continue our series of learning signal processing in Matlab. For that we have to go to the Matlab website and yeah, we have to go to this platform which is Matlab, and then we have to go to the courses. You can see here you can start exploring training, and then you will set back to this area where you can learn various type of courses. But our current course is this filter design and analysis method. Analysis method. So for today's session you will hear some type of noises, background noise, so please ignore that because there is a festival in India, and some peoples are singing for enjoyment, so you can hear a background noise of that singing. So please ignore that. Now we have to go to the session introduction, and then we will complete this whole you can see here this alone filter analysis is of 0.5 hour, which is 50 minutes total. So let's start this course without any delay. And okay, so let's start with the introduction.
Most real-world signals are plagued by noise or unwanted frequencies, making it challenging to analyze the signal and retrieve relevant information. Filters are used extensively in signal processing to remove noise, enhance signal quality, and extract relevant frequencies. In this course, you'll design two main types of filters: finite impulse response and infinite impulse response filters. It's important to choose the right filter for the desired application. An FIR filter introduces equal delays to all frequencies, preserving the signal shape in the time domain, while an IIR filter may unpredictably alter your signal's shape or timing. So the choice of filter depends on your needs. Go for FIR filters if the application calls for preserving signal shape, stability, and design flexibility. And choose IIR filters if you need to prioritize computational efficiency and lower filter order.
Okay.
If you want to design a filter,
So basically FIR filter used where the system needs proper signal and proper signal structure, and if you want to increase the computational efficiency, means if you want the filtering process to be very fast, but you can tolerate the unstructured signal. It is not unstructured, wait a minute. Yes, so if your priority is computational efficiency, then you can use IIR because it is fast, but it decreases the filter value
or filter order. If you want to design a filter using the standard parameters, there are functions and apps in Matlab to do that. It's important to understand the impact of a designed filter on signals. Filter responses provide insights into how various frequencies interact with the filters, which in turn help you make better design decisions. An often overlooked but crucial aspect of filter design is understanding and compensating for the delay that a filter can introduce. This delay can impact the timing of your signal. Learning how to compensate for it is a key skill for any filter design method. There are functions in Matlab that do this. By the end of this course, you'll be able to choose the right filter design method that best fits the needs of your signals, ensuring an informed and practical decision. And with that, let's get started.
Okay, let's get started. So we will learn about this. In this course, we will learn to design digital FIR and IRR filter using common filter response type with a set of specifications or a preferred design algorithm. Okay, visually filters characteristics in visualize filter characteristics in different domain to analyze how the filter modifies the time and frequency domain, and after that apply filters to practical scenarios such as frequency isolation and signal enhancement to achieve desirable signal. Okay, so let's see, verify watermark for this. Okay, power signal, frequency is in kilohertz. Sometimes watermark can be very small, or sometimes it can be very large.
There are 4 main specifications to consider when designing a filter. Let's see a quick refresher of each specification using a low-pass filter. The passband frequency marks the power that you want to keep, and the stopband frequency marks the power you want to remove.
Okay, nice. This is nice. We can use passband and stopband frequency to set a range of the signal or to bound the signal. My pen. Okay, so signal is like this, then
The transition band is in between.
ट्रांजिशन बैंड भी आता है भाई. There is 3 types of band we have to use, that is pass band, transition band and stop band. For passing the frequency from a point we have to use a pass band, and to stop the frequency at a point we have to use stop band, and in between the frequency in between the pass band and stop band will be denoted by transition band. Okay, transition band. Okay,
You can change the passband or stopband frequency to control the width of the transition band. The passband ripple is the size of the deviation allowed in the passband. On the other end, the stopband attenuation specifies how much unwanted power the filter will remove in the stopband.
okay,
If you increase the value, you'll remove more of the unwanted frequency content. The filter's order, or the number of coefficients, depends on the other specifications. Loosening the other specifications usually means a lower order, and tightening them means a higher order. Filter order matters because if you're going to deploy your filter to hardware, you're only going to have a certain amount of storage space and computational resources. So if the filter is too long, it won't fit on the chip. If you aren't deploying the filter, there are still other downsides to a longer filter. For example, more coefficients still means a longer computation time. In a perfect world, you could have it all. But in reality, if you want to improve one specification, the others may worsen. This means that you need to decide which specifications to prioritize, which will depend on your application for the filter.
Order number 5, obviously.
In this module, you'll practice designing different types of filters, so you'll be prepared for any situation.
This is nothing but a control system. You can see, to control the system we have to add a feedback, and by comparing the output of a system passing through a feedback network, then we have to compare that output of a feedback network in a comparator. Then we have to give the input of that comparator's output to the system. It is confusing, I know, but sometimes you just have to understand the system by diagram. You can see this is FIR filter and this is IR filter. So here you can see the efficiency will be perfect because there is a feedback configuration and this is a closed loop system, while the FIR system will be fast, but the problem here is it is open loop system, so there will be more noise present in this type of signals, sorry, this type of filters. So FIR filter and IIR filter. Sometimes you have to just understand what does the diagram tells about the topic. So if you understand by just looking at the diagram, you don't have to read all of this text here. You will just understand by looking at the diagram. X input, Y output, but that is connected in a filter network, sorry, feedback network. We have to again connect that feedback to the system's input. Y dash, this is passed output. Why? The FIR is a simple type of filter which will just use the system function, means it will take the input X and then it will do some processing or filterization in the system block and then it will give an output. So today we are going to complete 30% of this course, so it will be very easy for us to understand each topic step by step. What we have to do: add a filter design task to the live strip and select the bypass filter, sorry, bandpass FIR filter. So what we have to do, we have to just go to the task, then we have to select design filter, this option. Okay, so you can see there are different types of filter, but we have to select the bandpass filter. So I have selected the bandpass filter. Okay, once you selected the bandpass filter, FIR, yep, you will see a filter option and the variable in which it is stored. Okay, for now use the default value for all the parameters. In particular, ensure that the filter's variable name design filter. So filter variable name is design filter. Yes, filter variable name is design filter. So we have to click on submit and you can see that our signal is here, which is in phase as well as in magnitude. working. Sometimes it doesn't work. I don't know why. I clicked on run. DESIGNED FILTR equals to Matlab. This is perfect. We have to see the solution that what we are doing wrong here. Okay, so you can see we have to get signal like this. What did we do wrong? Ah, okay. So we click on reset. In task 1, we will go to task and we will click on design filter. It will get open. Then we will use FIR band stop. There are band stop and band pass. We have to select the band pass filter. Sorry, previously I have selected the band stop filter, not band pass filter. That's why we are getting the. Okay, you can see now we have proper input, but why? Oh, it has to be named as filter, not to. It doesn't need. After that, what we have to do? Apply the bandpass filter to the watermark flute audio signal mark. Name the result by OK. So we have to use this. Okay, we have to use this command here. So we will use this. Output name should be y out. The signal is marked. MARKE. Marked, and one is DESI design filter. Okay, so the value is assigned to y out. Next, we have to use pledge function here. Pledge, not pledge. Use pledge function to see the power spectrum of the filter flute sample. So we have to write here y out, out, and we will use a default value for watermark, window, and NT-FS, which is nothing but a discrete time Fourier transfer, and FS is our default sample rate, or you can say selected sample rate in a Matlab workspace. So our next task here is to specify frequency parameter, change the frequency unit to hertz, then set the sample rate to fs. Okay, so first of all we need to do something about the. Okay, what we have to do, under specified frequency parameter, this is a specified frequency parameter, change the frequency unit to hertz. And how can I do that? I don't know. How to change the. Okay, so I have changed and select sample rate, which is fs. Okay, design the minimum order band pass FIR filter. The band pass frequency should be this and this hertz, and use this and this hertz as a stop band frequency. So the stop band frequency should be 2001, and stop band frequency should be 2600. 2600. And why it's not perfect, I don't know. So band of, sorry, pass band, pass band frequency should be, I don't see, 2200 and 2500. 2600. Okay, why we are getting error, I don't know, but yes, the error is removed. You can see yes, you can see the magnitude and the frequency, the phase degree, both graphs are now much more filtered and clean. But there is one problem. Are the stop band frequency of the design filter correct? Stop band frequency. Stop band frequency. Stop band frequency equals to 2100, and next second is, yes, they are perfect. Perfect. Yes. Next, increment the amount of attenuation at the first stop band to 80 dB. This is the first stop band, so we have to write 80 dB. Then we have to run the program. After that, okay, so again we have to submit. $80 no? Yes, $80. Yeah, I don't want to read that. Or should we complete 50% of this course today? So next thing is create a band pass IIR filter. Name the filter as this. So now we have to use the band pass IIR filter. So which is this band pass IIR filter, and we have to name is that say don't need the number 2 here, and again we have to go to hertz, and after that we have to select the sample rate as fs, and then we have to click on the run button, and you can see there is an error, but we will solve that because the error we are getting because of this, the parameters. Again we have to set the parameters to 2 to 5, sorry, to 2200 to 2500 for passband frequencies. So 2200 to 2200. Okay, so the problem here is that we have to select each frequency step by step, then it will work, otherwise it will set to its default value after you change the frequency. Okay, so first of all what we need to set the passband frequency, sorry, stop band frequency. Then we have to set the pass band frequency, which is 2200. Then we have to set the pass band frequency to 2005, 100, and then we have to set these 2600. Okay, submit. Now you can see the noise is removed. This is our original signal, and you can see in magnitude or phase degree, you can see the noise is perfectly removed, and this is our watermark. Other section. Okay, so 30% course is already completed.
As you've seen, it's not possible to design an ideal filter. Instead, you need to choose specifications that describe what's good enough for your application. So, how are those specifications used to design a filter? Well, that depends on the filter design method. Let's walk through how one of the simpler methods works. Windowing can be used to design FIR filters. In this design method, start with your ideal frequency response. Sample it, and use IFFT to calculate its impulse response. The ideal impulse response is a very long filter, so you'll use a window to truncate it. If you use a rectangular window, this is your designed filter. Then you can calculate the frequency response of the designed filter to see the effects of the window.
Okay, so I am skipping this part because I don't understand what is meant by windowing and window. That's why. So I will just go to the next task, and there I will understand what is window or windowing by doing some tasks. Okay, so this is our signal. Okay, the 40% course is already over, so I just skipped the windowing part because I don't know what is windowing or window, because I didn't study about that yet.
How do you determine the impact of filters on signals in the time and frequency domains? You could just filter the signal and see what happens. But what if you have multiple signals? You can understand how a filter affects any signal by examining the filter responses, like the impulse, magnitude, and phase responses. Let's feed a signal that has a single spike at one point, called an impulse signal, to a low-pass filter.
Okay.
The filter's response to this signal is called the impulse response.
Yes.
Each point in the impulse response represents the filter's reaction at a specific time. For low-pass filters, the impulse response typically shows a slow decaying pattern. A divergent behavior in the impulse response indicates an unstable filter. Now, let's feed sine waves of different frequencies to the filter. The magnitude response tells us how the filter affects the amplitude of different frequencies in the signal. Ideally, a filter has a flat magnitude response in the passband, preserving the original signal's amplitude. However, the passband ripples can distort the signal's shape and cause it to lose its actual content. If you look at the stop band, you'll spot some dips there. This indicates an uneven attenuation in the stop band. For example, in noise-canceling headphones, analyzing magnitude response helps maintain audio fidelity by ensuring all frequencies are delivered at the correct levels. The phase response shows if there's a shift in the timing of the signal after filtering. This shift, called the group delay, indicates the time delay each frequency experiences due to the filter. Up to 100 Hz, you'll notice the phase response has a monotonically decreasing pattern, and then has a zigzag form. Within the passband, a linear phase means every frequency is delayed equally. However, a nonlinear phase in the stop band causes varying delays across frequencies. In applications like radar location tracking systems, even a minor phase shift can be critical. Understanding these responses gives you a holistic view of the filter's behavior. It's not just about knowing the equation. It's about understanding the story the filter tells in the time and frequency domains.
Okay, so I only understand about 50% of this whole video. Okay, so what we have to do here, we have to use the command window. Task 1. The first live task, design the bandpass filter. Okay, so we have to go here and then we have to select the design filter, but the problem is that I think it is already selected. Yes, the task 1 is also selected. Under the display filter option, select the impulse response. Impulse response to view the impulse response of the FIR filter. Then I guess okay, so you can see the impulse wait a minute. The filter is not stable because impulse response is a signal. Impulse signal is a signal where its value is only available for just one point. But here you can see that if the impulse or delta signal is processed by the filter, we get the impulse response, but the impulse response has infinite value at different point. So, I don't know if it is perfect or not, but we will see about that later. What we have to do now in the second, so here we have to use the impulse response. Okay, so wait a minute. Okay, so you can see in IIR filter, the impulse response is much more stable, but still it is not perfect as we want. Or I think it is perfect because it is showing the real time response, sorry, in real life response, or you can say practical response. And I have studied about the impulse signal and impulse response for ideal version only, that's why I guess so. But if I am wrong, then this will lead to a greater confusion for the future learning. Let's see. Under display filter response, select the group delay. Group delay. So what is group delay? This is group delay where the value will be like DC. Next. I don't want to watch the code. The Matlab. Oh, come. This the signal contains two type of data, which is filtered and original. Save the number of delayed sample to a variable named delay. In task 1. Okay. Sorry. So what we have to do to get the number of delay sample from a vector, when the filter has constant group delay, every element in a vector is the same, so you can extract the first element. And what is GD? I don't know how to write it. I think I have to use this group delay and function delay, both function here. I have to use both of these functions, so yes, you can see I have to use both of this function. Sometimes if you don't understand, you just have to copy paste the code from the view solution option and you will understand what does it mean. It's like, first we take a output variable known as GD, in which the value is designer. Okay, so this is window and grid display. Okay, so it will the GD has a value of a desired FIR, which is this signal, and it's contain the value of group delays, means the number of delays in this signal, and that is stored in GD. And after that we store the value of GD1. GD1 is nothing but the delay number, delay, or the first value of delay we have stored in delay variable. Okay, it is bit much confusing, but it is also interesting at the same time. Modify YFIR by deleting number of delays sample from beginning of the signal. Control C, so you can see the best thing about Matlab is it can give you the perfect syntax. You just need to understand it, and if you don't understand what does the syntax says, then you have to go to the solution, and there you can understand what is the solution, and from solution itself you can understand what is the question. Burst delay equals to this, and what is mean by this square bracket? It is mean by a empty vector or a empty array. So what we are doing is we are setting the empty vector. Deletion require an existing variable, so this is an existing variable, I guess. Let's see the solution. Because I don't think that, yes, is there something wrong? Is there something wrong or not? Okay, you can see the delay value is 212. There are 212 times delay. Create a new time vector called this. Oh, and that correspond to the aligned filter signal. So I don't know what is aligned filter signal, but we have to TA DJ. Now instead of T1, I think we have to write YFIR. Let's see if it will work or it will give us the error. First of all, the AND operator must be within the array index. Yes, it is perfect. It's not perfect. Use the code example above using the existing time vector t as t1. Okay, so instead of t1 we have to just use t, and we have to remove the semicolon, so the result will be displayed on the workspace area. So you can see here, this time the values are perfectly stored into t adjacent. Copy the code that create the time domain plot from the top of the script. Modify it so that the second plot command use t adjacent instead of t. Otherwise, keep everything same. Okay, so what we have to do, we have to copy the code. Now we have to paste it, and we have to use t a d j instead of t. Oh shit. The problem is that for FIR there has to be different ADJ. For this we just have to use T. Let's see. Yeah, that is perfect. We'll go to the next section. You can see that sometimes the code itself has the answer, but sometimes you need to find out answers by seeing the solution. Now change the filter function to the felt function dfnx, where df is nothing but a signal name and x is a parameter, I guess. I don't know. How can I change the function when I don't know about the signal? Okay, task 1. So what we have to do here, we have to just copy paste this. So YIIR equals to filter, design and mark. Okay. First we create the filter function, then we change that filter function to felt function, and both function do what type of task, I don't know.
When you send an impulse signal through a filter, the output is the impulse response. Every filter can be represented by its impulse response. When you send an arbitrary signal through the filter, the output is a convolution operation between the impulse response and your signal. Let's walk through how convolution works. First, you flip the impulse response and place it next to the signal.
Yes.
This creates a neighborhood around a sample.
So convolution is a formula which is it is in the back of my brain. It is like convolution is like y equals to x of tau minus k. No, it is like y equals to x of tau into h of tau minus k.
You multiply the neighborhood element-wise with the impulse response and add the results. This is the new filtered value for that sample.
Okay.
You may notice that we're skipping the first 4 elements. We'll revisit these soon. To get the next sample, move the filter over 1 and repeat.
Yes. So you can also find this convolution value by matrix or tabular form. I remember it.
Applying the filter to every sample gives you a new filtered signal.
I remember this.
So, what about the beginning of the signal? There's not.
So each time you just left one part of the signal and calculate the other neighbors, you get a new value, and that new value will be convolution of your old signal with respect to h and with respect to h, x and h. Oh,
Not
it
enough
is very much
information for the full
confusing.
neighborhood, but we need values.
First of all, I will show you the formula for convolution. Convolution formula, and we are dealing with a discrete signal, that's why I will use dt. Okay, so yep, this is the formula. As you can, okay. So here the problem is that I mixed up the formula with a tau and a k. It is not like that. What you have to do here, it is simple. You have to just multiply y of n equals to x of n convolution of h of n, where it is equals to summation of infinity to k equals to minus infinity x of k, which is nothing but x of tau into h of n minus tau. And here instead of tau they used k. This is the formula for convolution. You can also solve the convolution by matrix or tabular form.
There to perform the calculation.
This is a tabular form to
We can
solve
fill
the
in a
convolution.
value like
I'm
0.
not going to waste my time on the convolution because I didn't understand. That's why. Save the filter order to the design filter to a variable named this. Okay, filter order. Control C, Control V, and O equals to this, and our signal name is DESI, designed FIR. Okay. Next, what we have to do, calculate the first 500 sample of impulse response of a bandpass FIR filter, name the output in HI and TI, then plot HI versus TI. So we have to use a square bracket, then we have to add the value HI and FI, which is nothing but the output of a function that we are going to create now. Then we have to use this type of functions syntax. Control V. Okay. DF. So DF is the name of signal, which is design field fire. This is a default window, and this is a default, or you can say a mentioned sample rate, and then the plot function. Oh, sorry. In plot function we have to use HI. No, we have to use TI and HI, which is TI and HI. Okay. Oh, I used FI here. TI. Now you can see the graph. Are HI and TI are correct? Yes. Graph is perfect, I guess. You can see the impulse response. Okay, so if not, then I have to use like this. HI comma TI. If it will be not perfect, then what we have to do, we have to just change the value of TI and HI here, or we should see the solution first. Sometimes our solution is perfect, there is some minor mistakes that lead us to the, okay, 500. The first 500. Okay, so the Windows value is already given here in the task, that is 500. We didn't include that, that's why we get the error. Save the time in a second of the filter TC. So TC equals to T bracket filter order. So what is filter order? Oh, what is our filter order? So the value of TC is perfectly stored. Then plot the filter signal this versus this, and then add a vertical line at TC. Okay, so plot plot T versus T comma YFIR, and then we have to use the function xline at TC. Okay, let's see. So now what will happen, a straight line at TC will be shown in the graph, you can see. Next, 62% course is completed. So today we will complete 100% of the course, so we can move to the next topic known as circuit designing. Calculate the first 200 sample of the impulse response of a band pass IIR filter. Name the output HI and TI, then plot HI versus TI. So again we have to use this function here. So first we have to use the square bracket, and then we have to use the given variable name. After that we have to write the IMPZ DES design IIR, because we have to use the IIR filter. So for IIR filter we have to use the IIR signal. For the value of n we will use 200,000, and for the sample rate we will use as mentioned or given sample rate. Then we have to plot TI versus HI. Okay, next, plot the filter signal YR versus T. Okay, so our module is near to completion, but it is still not complete yet. Let's see how much we need to complete more. MA Matlab on ramp self-placed course. In that, in my course, we have completed 68% of the course. We are at attributes, response, filter design and analysis. After that we have to complete the filter stability, and after that we have conclusion. Okay, what we have to do here, calculate the absorption value of each frequency value in FR. FR equals to absorption function of frequency. Frequency FREQ, frequency. Name the desired we have to use here FR, and we have to use WATER abs. Next, Create a plot with FR on the x-axis and the absorption value on the y-axis. Okay. PLOT plot FR comma absorption. Sorry, the value of absorption is nothing but the water. Sorry, WATE water apps. Absorption is a function. Yep. Next session. And with this, we have. Sorry, we will complete our attributes response. Okay, you can see we have to perform 6 tasks here. Design a 10th order FIR. Okay, how to do that I don't know. 75% is completed. Design a 10th order FIR underwater absorption filter using water apps as the desired magnitude. Name the coefficient vector B. So for this I don't know what is the answer, because what is mean by the 10th order I don't know. That's why we will just copy paste this module. Okay, so by 10th order I guess we have to use the FIR function. FIR to filter the whale recording whale. Name the result whale fit. Okay, so result should be this FIL filter, and the signal name is WHA whale. Filter is a perfect function. It is not an input argument. What is the head? Use the filter function. Yes, I used the filter function here. The inputs are BA. Okay, I don't know how to use the filter function. Let's check. The input should be A and B. So the input should be B comma A comma whale. Okay, next. Calculate the 125th point frequency of a absorption filter. Name the output in this. H comma F equals to FRE QZ B comma A comma Y12 comma FS. I think it will give us the error because it doesn't use. Oh no, it is perfect. Create a plot with 2 lines. Okay, the first line should be desired filter. So I know how to create a plot, but if I watch that how to create a plot, it will be the waste of time for me, because I know how to create the plot. Hold. First this plot will be created, then we will use hold on function which will hold this graph, then we will again plot a new graph which will be plotted in this graph because we use the hold on function, and after hold off the new graph will be printed separately. Increase the order of FIR to from 10 to 30. Task 5th. Okay, so here we have to use 30. Okay. Recalculate the coefficient vector b and a so that they contain 10th. Okay. So we'll use this. Control C. Control V. Order should be 30, I guess. Frequency is FR, and I don't know about the magnitude. What is the magnitude? I don't know about the magnitude. IMAG. What is the magnitude? I don't know. So if you don't know what is magnitude, just see the solution. Okay, so you can see here that FABs and water apps. Okay, FABS. FABS and WATRABS. Okay, submit. Next, with this we have completed the 80% of our course. Now only one thing is
So far, you've
left,
represented filters using
that is filter stability, which consists of 1, 2 and 3 module, in which we will first learn about the zeros and poles, which also is of 15-minute
coefficients. Zeros and poles are another way to represent filters. To convert from the difference equation to zeros and poles, take the z transform. Then in the z domain, you can take the ratio of the filter output, y of z, over the filter input, x of z, to get the transfer function. The zeros are located wherever the transfer function is 0. In other words, the roots of the polynomial in the numerator. The poles are located wherever the transfer function goes to infinity, or the roots of the polynomial in the denominator. In filter design, the locations of the poles are important because they determine your filter's stability.
So basically for this course we have to learn about the filter first, because I know about the signal but I don't know very much about filter. Calculate the zero poles and gain from the fire absorption. Okay, ZPK is also in a control system course, where P stands for pole, Z is, this function is there in a control system. Okay. Calculate the zero pole and the gain from FIR. Okay. So Z panel पे we have to use this function, Z plane, Z and P are poles and zeros, and K is I think constant. Create a normalized minimum phase filter. Name the coefficient vector B mean. Create a normalized minimum vector. how to create a normalized minimal vector. Name the coefficient bm. How don't know I don't know how to create a normalized minimal vector, because that part I guess is in the fundamentals of Matlab, and I didn't done that course. I, yes. Okay, next what we have to do. Save the zero pole of a new coefficient vector BIM to a variable named Z and P respectively. Respectively. And how to save that I don't know either. I don't know how to save that. I have to use that function I guess. Again, yes, this function again, and then we have to display the result of the signal. Then we have to again do the same thing in the step number 3. So here we use p in 1. I think this is a syntax that we have to use again and again and again. Create a group delay plot with 2 lines. First plot the group delay of a linear phase filter, then plot. Okay, I don't know how to do that. That's why I'm just copying and pasting the solution. So first one is this and second one is BIM. Okay, so I understand that the value of B is B and the value of B for the second plot is BIM. The value of A is 1 for both. 87% of course is already completed. How much we have to do now? 75. So the zero poles filter stability is perfectly completed. Now we are on IIR filter stability. Here what we have to do, again we have to calculate. Again we have to calculate the same function again and again and again and again. So again I think I have to use the hint. Yep, we have to use this function, and then we have to use this to visualize the zeros and poles. So tf2zpk is a function. Remember that we have to use this function to store the value of 0 and pole with the reference of A and B. Increase the first order by 100 in IR option, absorption filter, and pay the authentic attenuation attention to 0 and pole. So to set the order to 0, function convert AB coefficient to 0 poles. Again, I know how to do that, but it will be too much. I will tell you what this code is up to. So you can see that we used a UL walk function to increase the order. Oh, and this is the sample. Sorry, this is a frequency and this is a magnitude. Then again the a and b, the value of a and b is changed because the order is changed. So again we store that value in z and p, and after that we again plotted the z and p function. Sorry, and this for future practice. So with this our course is complete, and we are now, you can say, moderately professional in signal and system. Exit course, leave. With this is also completed and this is also completed. The best part of the course is that you can download the certificate for your plagiarism. Certificate number 29. You can see certificate number 29 and report number 29. Progress report number 28, I guess. Report number 28 and a single certificate of our core signal processing technique in Matlab. Certificate signal single dot pdf, which will be saved in certificate itself, mat certificate. Okay, so I think that will be perfectly done. So that's all for today. We will meet again in our next live stream. Till then, bye bye.